Welcome to the calculus level on exponential growth and decay. Now, when we're talking about exponential growth and decay, we're going to actually use a differential equation. So we might say something like dp dt equals kp. And what this is telling us is this is the rate at which a population grows. So the rate at which our population grows. And we're told that it grows proportional. So the k is the proportional part, proportional to the population itself, proportional to the population p. Now let me just make some sense of this for you. Let's say we have a town whose population is 500 people, okay? And let's say the number of babies born per year, so that would be our growth, would be 10 per year, right? Now let's say we have another town of 5,000. We could expect them to have 100 babies per year, right? If we go up to 50,000, maybe that's 1,000 babies per year. And so there's that growth rate is higher the bigger the town. So our rate at which we're growing is proportional to the size. We've got the same thing here in bacteria. So I'm told that if a population of a colony grows at a rate proportional to the population, then dp dt equals kp. That's what we just had. For example, suppose a bacteria population of 1,000 grows at a rate of 300 bacteria per hour. How fast would you expect a population of 2,000 to grow? And we quickly see that we're just going to double, and this is going to be 600 bacteria per hour. All right, so any quantity whose rate of change with respect to time is proportional at that time can be represented by this equation. And we can solve this equation. So we know how to find the antiderivative here by separating our variables. So first we're going to say dy, and we're going to divide by y over y equals k dt. We're going to integrate both sides. And on this side, we're going to have the natural log of y, and on this side, we're going to have kt plus some c. And then we can solve for this, and we're going to get that y equals e to the kt plus c. And then it turns out that we can write this as y equals e to the kt times e to the c. And that c is our initial value. I'm going to call it y sub 0 e to the kt. That's our starting population. So that's the initial population. And t is our time right there. All right, so what we're going to be doing in these problems is we're going to actually just jump from here, from this equation, right over to that equation. All right, so let's start with this one. So our bacteria culture starts with 500. Bacteria grows at a rate proportional to its size. As soon as we hear it grows at a rate proportional to its size, we know that dp dt equals kp. And if that's the case, that means that p equals p sub 0 e to the kt. P sub 0 is that initial population. So I'm going to say, okay, my population equals, it started with 500. E to the kt. Now the next bit is a clue to figure out this k. After 3 hours, there are 8,000 bacteria. So I could put in 8,000 here equals 500, and I'm going to put in 3 hours, k times 3. So first I'm going to divide 8,000 by 500, so that'd be 16 equals e to the 3k. And I take the natural log of both sides. Natural log of 16 equals 3k, and then I'm going to see that k equals the natural log of 16 over 3. If you prefer a decimal, you could do that as well, but here's our equation. P equals 500, e, our k, is natural log 16 over 3 times t, and we have written an expression. Okay, part B asks us for the number of bacteria after 4 hours. Let's grab that equation we had here. Let's see how good it's in one chunk. So we're going to copy that and bring it over here. And let's see, put it right over here, paste it in. And all I have to do now is plug in 4. So I'm going to go in here, and P equals 500 e to the natural log 16 over 3 times 4. And now it's just calculator work. So I can pull up my calculator, 500 second e parentheses ln of 16. I need to divide that by 3 and then take it times 4. And I'm getting 20,158. So 20,158 bacteria. All right, next question asks when will it reach 30,000? This time 30,000 goes in here. I've got 500 e to the ln 16 over 3t. First step is to divide by 500. So 30,000 divided by 500 is going to give us 60. So 60 equals e to the ln 16 over 3t. I'm going to take the natural log of both sides, so I get natural log 60. On this side, the natural log just gets rid of the e, so I've got natural log 16 over 3t. Oops, natural log of 16 divided, let me write that again so it's clear. So that was the natural log of 16 over 3t. And then last thing is to come over here. Since I wrote this natural log 16 over 3, I can multiply by the reciprocal. So 3 over natural log 16 times natural log 60, and now I can just put this in my calculator. So 3 times the natural log of 60 divided by the natural log of 16, and I have my answer 4.43. So T equals 4.43 hours. And let's make sure that makes sense. Let's see, we knew after 4 hours we were at 20,158. 30,000 is bigger than that, so I would expect my answer to be bigger than 4 hours. So that's good. All right, so we can have the same thing when we're decaying. So radioactive substances decay at a rate proportional to their mass. And so let's take a look at this problem. So polonium-210 has a half-life of 140 days, and we're asked to find a formula. So we're going to start with that same formula, and I can use whatever letter I want. We can continue with P. So P equals P sub 0 e to the kt. Sample has a mass of 200 milligrams, so that's what I'm starting with. P equals 200 milligrams, and I have a half-life. So after 140 days, half of that is left. That means that P is going to be 100 when my time is 140. Divide by 200, so I got 0.5 equals e to the 140k. And then I can take the natural log of 0.5 equals 140k, and k equals the natural log of 0.5 all over 140. Now I know last time I kept it exact values. Let's just for once, we'll get a decimal. So that means k equals, let's see, it's negative 0.00495. We don't want to round this too much, otherwise our answers will be way off. All right, so we've got a formula. P equals 200 e to the negative 0.00495 t. All right, so I think we'll have another question. The mass after 100 days, we want that formula. So let's grab that. I'm going to copy that and come over here. All right, and so after 100 days, all we have to do is plug in 100. So let's P equals 200 e to the negative 0.00495 times 100. So let's check that out. 200 second e to the, let's see, negative 0.00495 times 100. And I get 121.9. So 121.914 if I want to round to 3 places. And this is going to be milligrams. Now let's make sure this makes sense. So if we go back here, we had 200 milligrams, right? So on day 0, So this is days and this is milligrams. On day 0 I had 200, and we know that it takes 140 days to get half. So day 140 I'm going to have half of that, which is 100. So day 100, that makes sense. 121.914 had better be in between these two values because 100's in between 0 and 140 and 121 is between those two. All right, next question asks, when will the mass be reduced to 10 milligrams? Let's carry on our chart to get an idea of when that would happen. So day 280, we'd be down to 50. And then I keep adding 140, so the next one's going to be day 420. I'm going to be at half of this, 25. And then I add another 140, so day 560, I'm at 12 and a half. And so day 1000, let's see, 120, I'm going to be at half of that, 6.25. We're going to expect our answer to fall in there because the 10 is in there. All right, so let's give this a go. 10 equals 200 e to the negative 0.00495t. Our first step is to divide by 200. So 10 divided by 200 gives us 0.05 equals e to the negative 0.00495t. I take the natural log of both sides. Natural log of 0.05 equals negative 0.00495t. And then t, I'm just going to divide those numbers. So I've got natural log of 0.5, and I divide it by negative 0.00495. And my answer comes out to 140. That doesn't look good. Ah, I see my problem. I entered in 0.5 instead of 0.05. Let me try that again. There we go. 605. That looks a lot better. 605 is my time. If I don't round it, it's 605.198. But so about 605 days, which fits right in there. So that's good. All right, we can do the same thing with our bank account problem. So let's take a look at this one. A bank account earns interest continuously at a rate of 5% per year. Initial deposit is 1,000. No other deposits or withdrawals are made, and we're asked to write a differential equation. So our differential equation would be that the amount in our account is changing at a rate of 0.05 of the amount. Okay. So 5% of the amount gives the amount of change. So there's that. And now it asks me to solve that differential equation. So let's go ahead and just grab this for a minute. So we're going to copy that, bring it over here. And we want to solve that equation. Well, remember, we already know that the solution is going to be in the form a equals a sub 0, our initial amount, e, and I know this k value, 0.05t, so I'm good to go there. I have solved it. They give me an initial amount I can put in there. Oh yeah, $1,000. So let's do that as well. So a equals 1,000 e to the 0.05t. So part C asks, when will my balance be 2,500? I'm going to put 2,500 right in here. 1,000 e to the 0.05t. Divide by 1,000. 2.5 equals e to the 0.05t. Natural log of both sides. And last thing, we just divide, and we can see that the natural log of 2.5 divided by 0.05, and we can see it's going to take 18.3 years for our $1,000 to grow to 2,500 strictly with 5% interest. All right, good luck on your homework.